In Chapter 6, we're going to be taking a deeper look at the atom and particularly focusing on what's happening with the electrons. When you hear the term electronic structure, that's simply referring to where electrons are located and how much energy they have. We're going to start with a discussion of waves, which this may seem like an odd place to discuss waves, but once scientists understood that electrons are moving in wave patterns, our understanding of what's going on inside the atom really started to explode. Electromagnetic radiation is just a type of energy that moves using waves. Light is one type of electromagnetic radiation. Let's take a look at some of the properties of a wave. The highest point of a wave is called the peak. The lowest point is the trough. The distance between two peaks is the wavelength. If you pick one point on a wave and count how many times per second that point passes you in different waves, then that would be the frequency. So frequency is the number of complete waves passing any point per second. Here is some of the same information on a more traditional sine type wave. Going from peak to peak is the wavelength. You should be careful when you're looking at wavelength. If you need to go from either peak to peak or trough to trough. If you go from midpoint to midpoint, that is just half of a wave. You'd have to go from here to here to get the whole wave. Wavelength and frequency are inversely proportional to one another. So as one gets larger, the other gets smaller. And you can picture that with the figure before you. Here you have a longer wavelength. Less of these waves could pass in a second than these waves. This has a higher frequency but a shorter wavelength. There are several different types of electromagnetic radiation. The part that we can see, visible light, is just this small area right here on the spectrum. You've got gamma rays with a really, really short wavelength, and then radio waves with a much larger wavelength. In between those, you have X-rays, ultraviolet light, visible light, infrared, and microwaves. Visible light can be broken down into the rainbow. The rainbow is made up of different types of light at different wavelengths. Now, for all of these types of light, the speed or the velocity is the same. So no matter what type of electromagnetic radiation you're talking about, the speed is 3 times 10 to the 8th meters per second. So the property of the wave that differentiates your different types of electromagnetic radiation is the wavelength. You've got shorter here, longer here, but they all have the same speed. Let's talk a little about this formula. C is the symbol used to represent the speed of light. This symbol is lambda, and it's used to represent wavelength. The symbol is nu, and it's used to represent frequency. So the speed of light would remain constant. As lambda wavelength increases, frequency decreases. The top wave in this picture has a high wavelength but a low frequency. This one has a low wavelength but a high frequency. So as one gets larger, the other gets smaller. On your electromagnetic spectrum, you have higher wavelengths far to the right, which means this is the lowest frequency, and the same thing works for the color spectrum that you have here. The highest wavelength is on the right, the lowest wavelength is on the left. During the 1800s, scientists were doing a lot of experiments with light, and they knew that light seemed to move as a wave. But that didn't explain several things that they observed about light. For example, they wanted to explain why something heated gave off light. These scientists began looking for a relationship between the temperature of a substance and the type of wavelength of light that was being given off. A scientist named Max Planck made an assumption that went a long way towards explaining that relationship. He said that energy comes in packets, which we call quanta or quantum. So an atom can't gain or lose just any amount of energy. It's going to gain or lose in certain multiples of an amount of energy that Max Planck discovered. It's called Planck's constant. Planck's constant is 6.626 times 10 to the negative 34th joules seconds. And so atoms are going to lose or gain energy in some multiples of that number. A couple of different ways you could think of this. Look at the man on the ramp. A ramp is continuous. You can be anywhere on that ramp at any point in time. Whereas steps, you've got to be on a step or on the next step. You can't be halfway in between. If we lost weight the way an atom loses energy, we would go out and run for days and days and days, and your weight would stay exactly the same until all of a sudden you hit just the right amount and you drop 5 pounds at once. So that would be losing weight the way that an atom loses energy. It's got to be in specific amounts that we call a quanta. I do want to point out that Planck's constant is a really, really tiny number. Times 10 to the negative 34th, you would have a lot of zeros in front of this number. And so because that number is so small, we are pretty unaware of the fact that energy is gained and lost in this amount. But it makes a big difference to an atom when you look at how tiny an atom is. All of a sudden, this is they're kind of on the same scale when you have a really tiny atom and a really tiny amount of energy. Einstein used Planck's constant, or Planck's discovery, to explain the photoelectric effect. This effect says that when light hits a metal surface at a certain frequency, it causes electrons to jump off of the surface. So this light is providing an energy and providing enough energy to those electrons that they're no longer attracted to the protons where they were. They're getting pushed off the surface. For different metals, that requires a different amount of energy. And so for different metals, they were finding that a different frequency of light was required to make this happen. Einstein recognized that that had to do with the quantum nature of light. The formula that he used is that the energy is proportional to the frequency. So you've got energy equal to h, which is Planck's constant, times frequency. So all of a sudden they're recognizing the relationship between energy and frequency. Keep in mind that Einstein was a physicist. He would have had an excellent understanding of the fact that force is equal to mass times acceleration. Now this formula is not part of your curriculum. I just had it up here to make a point that for Einstein, in order for something to put a force, it needed to have a mass. And this light was putting a force on these electrons. So that was something that he really would have needed to explain to make what he was observing fit into the scientific understanding that he had. This is one of many experiments where scientists were observing light acting like a particle. It's something with a mass to it. So this kind of begins to get into what we call the dual nature of light. We say that light acts both like a wave and like a particle with a mass. When you think of it in terms of a particle, we call it a photon. A photon is a particle of energy that makes up light. So light acts both as a wave and as a particle.